Recently, we've been talking about the concept of stabilizability, especially for LTI systems. And what stabilizability was that a system or a pair AB, I'm talking about an LTI system, the system XL equals AX plus BU is stabilizable if all the solutions can be made converge to the origin by some proper choice of control input signal. Okay. A formal but equivalent definition was that a system or a pair AB is stabilizable if the uncontrollable dynamics that appears in the controllable decomposition, so I'm talking about the AU matrix, is exponentially stable. Okay. And then we also introduced in our previous lecture a very elegant test for stabilizability, which was in a sense the generalization of the eigenvector test for controllability, which said that a system, a pair AB, is stabilizable if and only if no eigenvector of A transpose whose eigenvalue is with a non-negative real part belongs to the null space of B transpose. Okay. And in this lecture we will continue with yet another test for stabilizability. Okay, this is our Lyapunov test for stabilizability. Given the system LTI of order n, okay, it's stabilizable if and only if a Lyapunov inequality is satisfied in the following sense. There is a symmetric positive definite matrix P. Okay, so P is a real square matrix n by n. Okay, n being the order of the system that satisfies the following Lyapunov matrix inequality. The following Lyapunov matrix inequality. Okay, so it's AP plus PA transpose minus BB transpose less than 0. This less than 0 means that, note that this here is a matrix of size n by n, and also it's a symmetric matrix by construction, and Lyapunov test requires that if a system or the pair AB is stabilizable, then we should be able to find a matrix P, okay, symmetric positive definite, such that when using that matrix, when we construct this n by n matrix, which is also symmetric, that matrix is negative definite. Okay, so let's call this inequality 1, and it has a very nice extension to the discrete time case, which is not difficult to figure out. Now let's talk about the proof. We will only talk about one direction, so this is an if and only if result, so we're gonna be talking about only a single direction. For the other direction you can go and check the textbook. It's a little subtle but definitely understandable. Okay, so let's begin our proof. Okay, part 1, inequality 1 implies stabilizability for the system. Okay. Now, so we start from this condition. Okay, suppose that we have a P symmetric positive definite, and that P satisfies this inequality. Okay, and then from there we will reach the conclusion that the pair AB must be stabilizable. And to do that, we will use the recently introduced eigenvector test for stabilizability. Suppose there exists a symmetric positive definite matrix, an n by n matrix, P, that satisfies inequality 1. Okay. And then let X be a vector. In fact, let X be an eigenvector of A transpose. Okay. Let X be an eigenvector of A transpose such that A transpose X equals lambda X. Okay, and the corresponding eigenvalue lambda is such that it's on the closed right half plane with the real part of lambda being non-negative. Okay, and then if we can show that this vector X, this eigenvector, cannot belong to the null space of B transpose, then by eigenvector test we will have established stabilizability of the pair AB. Okay, so let's go ahead and do that. Okay, then we proceed as follows. Write B transpose X norm square. Okay, so we start with this, which can be written as X conjugate B transpose S. This X, remember this notation, this means conjugate transpose. Okay, since B is real, we don't require conjugate transposition because they're the same thing, transpose and conjugate transpose for B. Okay, so this norm square can be written in that form, and then that's greater than, strictly greater than this. Okay, X conjugate transpose AP plus PA TX. Okay, because P, A, and B, they satisfy this matrix inequality. Now let's play with these terms here. Let's reorganize them. That we can write as A conjugate transpose X, and then together we take conjugate transpose once again. And since A is a real matrix, conjugate transpose and transpose, they mean the same thing. Therefore, we keep transpose sign there. So we have A transpose X conjugate transpose. So it's X conjugate transpose times A, so times P, and then X is coming from the other side. And for the second term, we have X conjugate transpose P, and then we have what? A transpose X. Okay. Okay, and here we use the inequality 1. Now, A transpose X is lambda X, because X is not an arbitrary vector, but is an eigenvector of A transpose. So that produces, this is lambda, and then we're taking lambda times X, then we're taking its conjugate transpose. So it would produce lambda conjugate times X conjugate transpose. Okay, lambda conjugate, and then X conjugate transpose, and we can write that as X conjugate transpose PX. And here we have lambda X. Lambda is a scalar, we can carry it to the front of the term and write lambda times X conjugate transpose PX. Okay. Now here we have X conjugate transpose px, and here we have x conjugate transpose px. Therefore we can combine lambda star and lambda in a single parenthesis, and that will be multiplying x conjugate transpose. Okay, so that equals lambda conjugate plus lambda times x conjugate transpose px, and that equals 2 times real part of lambda times x conjugate transpose px. Okay, now the real part of lambda is non-negative, therefore this thing here is non-negative. X is an eigenvector, therefore it's a non-zero vector, and P is a positive definite matrix, therefore x conjugate transpose Px is necessarily a positive real number. Okay, so this is positive. So a non-negative number multiplying a positive number, the result is a non-negative number. So what we have obtained is that the norm square here is strictly greater than, okay, something that's non-negative. Okay, therefore this thing must be strictly positive. Okay, so let's call this inequality 2. Okay, so basically we have proven this direction, because if the norm square is strictly positive, that means norm is strictly positive. If norm is strictly positive, then what's being normed must be non-zero. Therefore B transpose X cannot be 0. That means X cannot belong to the null space of B transpose. Therefore the system by eigenvector test has to be stabilizable. Okay, so let's finish that part. So the inequality 2 implies that norm square of B transpose X is strictly positive. Therefore the norm of B transpose X is strictly positive. That implies B transpose X cannot be 0 vector, and that implies X is not in the null space of B transpose. So that implies system stabilizable by the eigenvector test. Okay, so that establishes part 1. For part 2, where stabilizability implies the Lyapunov inequality 1, see the text. Okay, it constructs basically a P. The symmetric positive definite matrix that appears in the inequality. See the text. Okay. Now let's let's talk about a very nice application of this stabilizability test through the Lyapunov inequality. So that's what we will do now. Namely, we will talk about feedback stabilization through Lyapunov test. For that, let's start with a stabilizable system. So let x dot equals ax plus bu be our system of order n. Okay, and suppose that the size of the input vector is k. So this system we assume to be stabilizable. Okay, therefore there exists a symmetric positive definite matrix P such that the Lyapunov inequality, which is AP plus PAT, strictly less than DB transpose, is satisfied. Okay. Then, okay, let me write what I just said. There exists a P transpose such that AP plus PAT minus BB transpose is a negative definite matrix. Okay. Now, if you have an excess to such P, then using that P, you can obtain a stabilizing feedback law. Okay, U equals minus Kx, under which the closed-up system, whose matrix would be A minus BK, is exponentially stable. Okay, and this is how you would construct the feedback law. Define, or the feedback gain, define K as 1/2 B transpose P inverse. Okay, so K must belong to what? B is an n by K matrix, therefore B transpose is K by n, and P inverse is n by n, so K by n times n by n, so that produces a K by n matrix. Okay, so K is, well, capital K is a K by n matrix. Okay, now the claim is that this feedback gain can be used to exponentially stabilize the origin of the system. Okay, so here let me write the claim. U equals minus Kx is a stabilizing feedback for our system x that equals Ax plus Bu. That is the closed-up system which is formed under this feedback, that is plug in U equals minus Kx. What you have is x that equals Ax minus Bkx, and that can be written as x that equals A minus Bk multiplied by x. X that equals A minus BK x. So that's our closed loop dynamics, where the loop is closed with this feedback law, U equals minus Kx, and where K is obtained through this relation, where P satisfies the Lyapunov inequality for stabilizability. Okay, now this is not at all obvious that this K will stabilize the system, but it's very easy to establish that, to show that. So let's do that. Okay, now this claim holds true because of the following argument. Here is the proof. We start with the Lyapunov inequality, okay? AP plus PA transpose minus B transpose is a negative definite matrix. Okay. And then this term can be written as follows: AP plus PA transpose minus 1/2 BB transpose and minus another 1/2 BB transpose. Okay, so what we did is we wrote this minus BB transpose as minus 1/2 BB transpose and another minus 1/2 BB transpose. Okay, looks like a stupid step, but it's not. Oh, if you introduce here something else, namely the identity matrix. Now, here we write the identity matrix as P times P inverse, and we do the same thing for the other term on the other side, okay? BB transpose times P inverse times P, another identity matrix, okay? So clearly, this line here is a more complicated way of writing the above line. But writing this expression in this more complicated way has a payoff, and it's the following. This thing you can write as the following. Okay, we have, okay, so we have this term AP and also this term. Both of those terms are multiplied from right by P. Therefore, we can write this term and that term together with something times P. Let's write that something. That something is 1/2 B transpose P inverse. Then we have P. Okay. So this takes care of this term, AP term, and the second BB transpose term. And then as for this and that, both are multiplied by P this time from left. So let's also write that as P times something, and that something is no other than A minus 1/2 BB transpose P inverse, and then transpose. Okay. And then what we have is the following. Remember that we introduce K as this matrix, 1/2 B transpose P inverse. Therefore, we have 1/2 B transpose P inverse, a K here, and also 1/2 B transpose P inverse, another K. So we can write with our newly introduced notation this as A minus BK times P plus P times A minus BK transpose. Okay, so what we have obtained is the following. Some matrix, closed-loop matrix, okay, let's call it A tilde. A tilde P times, A tilde P plus P times A tilde transpose is a negative definite matrix, okay? So if you remember the Lyapunov test for exponential stability, that test will tell us that this matrix, okay, must be such that all the eigenvalues are with negative, strictly negative real parts, okay? So that's our inequality one. So that means the system X, or let's call it Z dot equals this matrix, A minus BK transpose times Z, is exponentially stable by Lyapunov test for stability. And then if the system Z dot equals A minus BK transpose times Z is exponentially stable, that means the matrix A minus BK transpose has eigenvalues all with negative real parts. Since a matrix and its transpose has the same eigenvalues, if you transpose A minus BK, you obtain A minus BK, and this tells us that A minus BK must have all the eigenvalues with negative real parts. And that means the closed-loop system is exponentially stable. Okay, so inequality 1 implies by Lyapunov stability theorem that Z dot equals A minus BK transpose Z is an exponentially stable system. Okay. Hence, all the eigenvalues of this matrix is with negative real parts, and then all the eigenvalues of A minus BK are with negative real parts. Hence, X that equals A minus BK X has to be exponentially stable also. Okay, so that's the end of our demonstration. Okay, so by through this claim we have shown something, and what we have shown is, well, we knew it more or less already. What we have shown is that if a system is stabilizable, okay, then by some state feedback law, it can be, the closed-loop system can be made exponentially stable. Okay, so let's write that conclusion formally in a theorem. Okay, so we have obtained the following: AB stabilizable, okay, implies there exists a K as a feedback gain such that the system, the closed-loop system A minus BK X is exponentially stable. Okay. Now, when you're dealing with LTI systems, almost always, if you have some condition, then if you have an implication, the reverse implication also holds true, usually, not always. So this is one of those cases, that is, we have shown through that simple claim this direction, but the other direction is also true. So in fact, if you can find a stabilizing feedback law, then your system is stabilizable. Okay, so that's this result is true both ways. Okay. Now, if your system is not just stabilizable but controllable, that is, if it satisfies a more restrictive condition, then you can say a lot more, or you can claim a lot more about the structure of A minus BK. Okay, you can. Okay, we know that we can claim that A minus BK by some proper K can be made exponentially stable, but if your system is controllable, or if the pair AB is controllable, you can not only make A minus BK exponentially stable, but you can place the eigenvalues of the closed-loop system matrix A minus BK to anywhere you like, okay, by a proper choice of feedback gain. So that's also an important theorem. And there's a command in MATLAB which you can use for a controllable pair AB. I'm pretty sure most of you have heard about it. It's the command called place. Okay, so what you do is you just give that command your matrices A and B, and also you give the desired pole locations, eigenvalue locations, and it produces the feedback gain K, such that the eigenvalues of A minus BK are at locations that you desire. Okay, so let's also put that down formally as a theorem. Okay, now suppose the system x that equals ax plus bu be controllable, and suppose that its order is n. Okay, so x is in Rn and u is a vector of size k, is controllable. Then it turns out for all sets of complex numbers lambda 1, lambda 2, lambda n, okay? So just an arbitrary set of n numbers. These n numbers we will require to be the eigenvalues of our closed-loop system matrix. There's only one constraint on these eigenvalues, because we work with real matrices. If you have a complex or a non-real eigenvalue here, its complex conjugate must also be a member of this set. Okay. Other than that, we have no constraints whatsoever on this choice of n numbers, complex numbers, and where non-real eigenvalues, non-real lambda i's, must appear as conjugate pairs. Okay. We can find a feedback gain. Okay, a feedback gain matrix K of size K by n. K is the size of the input vector and n is the order of the system, such that Si minus A minus Bk. Okay, so then we take the determinant, namely the characteristic polynomial of the closed loop system A minus Bk produces the desired poles, eigenvalues, S minus lambda 1, S minus lambda 2, S minus lambda n. So this procedure of finding K, okay, where you can use command place in MATLAB, is called pole placement or the eigenvalue assignment. Or eigenvalue. Okay. Now, so for a controllable system, we can always find a feedback gain such that the eigenvalue locations are wherever we want for the closed loop system. But we have to be careful when applying or when using this theorem. For instance, when using the command place in MATLAB. Okay. Suppose you have a system x equals ax plus bu, and then you want the closed loop system to be stable. So what you, okay, if you don't think too much about it, it seems like it's a good idea to place all the eigenvalues at very negative locations. Okay, let's put them all at minus 1000. Okay, so that would mean the convergence would be really fast and everything is great, okay, from the stability point of view. But there's certain practical considerations that you have to take into account. For instance, if you place all the poles arbitrarily at very toward minus infinity, let's say at minus 1000, then that can be established, it's true, for a control system with some k, but that k probably will have very large entries. Okay, so that k will have a large norm in a sense, and a k with a very large entries would mean that this a minus bk will have large entries, and so that would mean, or since the input is, control input is u equals minus kx, large k would imply, even if you start close to the equilibrium point, it would imply large control inputs. Okay, if for instance you're driving your motor, so that would require large voltages, okay, large control effort for some time. Let's say let's say around 5000 volts, okay, which may not be in general realistic. You have to be you have to stick to the limit, let's say between plus 24 and minus 24 volts. Okay, so that's one thing you should be careful about, pole placement. The other thing that you should be careful about pole placement is has to do with the fact that, again, if k is large, because you pick diagonal locations arbitrarily to the left, large k would mean, again, large a minus bk, and that would mean large entries for a minus bk, and that may mean that even if you start close to the equilibrium point, you may have some very large overshoot. Okay. Now this large overshoot, even if you have no constraint on the control effort, would mean the following. If this is an approximation of a nonlinear system, if this is a linearization of a nonlinear system around an equilibrium point, with large overshoot, you will be kicked out of the region where this linearization is a valid approximation. Okay, when you're kicked out of that region where it's safe to use x equals ax plus bu, then everything could happen, and as a result, your stabilizing feedback law may not be actually stabilizing for the actual nonlinear system's equilibrium point. Okay, one example would be the pendulum. Okay, at the unstable equilibrium point, if you try to stabilize that system, okay, that equilibrium point, unstable equilibrium point, with pole place command in MATLAB, where you choose eigenvalue locations arbitrarily, then you'll most likely be unsuccessful with your design. Okay, that's why we use, instead of command place, we use like optimality-based pole placement methods, okay, to stabilize unstable equilibrium points, like a linear quadratic regulator. Okay, so even though this is a great theorem, we have to be careful about some practical considerations.